Okay, let's have a look at three-phase alternators. The last subject. All right, alternators. So these machines are designed to generate AC current, right? They convert mechanical energy from a prime mover to electrical energy. A lot of these prime movers include diesel engines, wind and steam turbines, and water turbines. Look here, we have a diesel generator, okay, or diesel alternator, technically. On the left here side, we got the diesel engine. On the right here, this guy on the right, that's the alternator, okay? We also have steam turbines. Okay, and the alternator is this little box on the far left. That whole stretch of the majority of it is all steam turbines. Now these steam turbines you'll find in coal generation, nuclear generation, natural gas generation, bioenergy systems. Anytime where you use steam to generate electricity, and the steam is created by burning something or heating up the water, you're going to see these steam turbines. Hydroelectric dams. Okay, this is what a hydroelectric turbine looks like. Down here at the bottom, we have our water inlet. Here's our turbine at the very bottom. Shaft goes up to the middle to the alternator. The alternator is up here. Okay, then water goes through our turbine, then out the water outlet. Okay. Now, what are they all doing? Well, we saw this little clip before. We have a three-phase alternator. We have, for this one design, we have our windings 120 degrees at a phase from each other, and the goal is to put a magnet in the middle so we can get our three-phase current out of it. Now, the connections for these alternators, they can be Y or delta connected, okay? Depending on the application and ratings. You know, if you think about it, if we keep voltage rating for insulation in mind, let's say we have a generated voltage of 4,800 volts. Well, that insulation rating for this winding, if it's Y connected, doesn't have to be rated for that higher voltage. It'll be √3 less, right? So if we have a 4,800 volt system, that's going to work out to 2,800 volts. Okay, so that's one advantage of connecting it as a Y. But the currents are going to be limited. Now if we have it delta connected, okay, and let's say this was generating about 4,700 volts, well, our current through this winding will be able to be higher to our loads because we have a delta connected system. So it's going to be specific to the applications or what design importance was for the person designing the alternator. Okay, now we have to have rotating fields. We're going to look at that in a moment, where we're going to have a field winding and either slip rings, well, typically slip rings. Now we have two types of alternators. We have a revolving armature type and a revolving field type. Okay, one is very common, one is it's a little more trickier, and you'll see why. So here we have a revolving armature type. By revolving armature we mean that the armature is getting the current and potential induced into it. Okay, so what we have here is we have our three-phase lines connected to the rotating part of our alternator here. Now the poles, the stationary side, we have a DC field. They are just north and south DC fields. So you remember back when you first looked at AC generation in year 2, we just had a simple loop going through a stationary magnetic field. That's what's going on here. Okay, there are some limitations though. So if we have that 4,800 volt alternator, rotating here with really high currents, we're passing all that potential and all that current through these slip rings because we have to get the electricity out of that alternator. We're going to put the current through these slip rings. So there's going to be brushes and there's going to be wear points and a lot of issues there. Okay, so it's not really a very effective design. Okay, so when we look at the revolving armature schematic here, we're going to have a Y, let's say, connected load, which is pretty common for that type of configuration to have a Y connected armature. Okay, and then it's going to be rotating, and we're going to have a stationary DC field. Okay, revolving armatures are, again, like I was mentioning, they're not used too often. Because the limitation of the output current has to go through brushes and slip rings, okay, that design, higher voltages, higher currents, not too effective using the rotating armature type. Okay, here we have the revolving field type. More common. You're probably never going to see the revolving armature type. Out of all the generators in the Lower Mainland, I'd say over 90% of them are this type of revolving field type. What we have here now is we have our three-phase windings stationary. Okay, they're in, guess what it's called? The alternator stator. Okay, and we have the rotating magnetic field here. Now just remember, all it needs is a DC current going through it because it's going to have the polarity of the rotor is going to stay north and south, and we're going to rotate it at a specific RPM. Now we have a DC supply. Again, we have two slip rings, but as you can imagine, the current doesn't have to be that high if we have many turns here. Okay, your old magnetism lessons you had last year, the strength of the magnetic field is proportional to the current and the number of turns. Well, if we have a small amount of current going through the windings and we had lots of turns, we're going to have a pretty strong magnetic field that's going to cut through our stator windings or our stationary armature. Okay. Now on the right here is a nice general arrangement drawing of what we're going to see. We're going to have in the middle, we're going to have a DC electromagnet. It's going to be on a drive shaft. We're going to have the conductors come out through slip rings. Okay, and those slip rings and brushes are going to connect to a DC power supply. And we're going to be able to adjust that power supply depending on what our voltage requirements are. Okay, we have our rotor here. We have our armature windings. Okay, they're stationary and they're situated 120 degrees, mechanical degrees apart from each other. Okay, and they're going to generate our three-phase AC. Magnetic field starts to rotate. Like we had that little animation there, the magnet rotates, it's going to induce three-phase electricity, each phase 120 degrees apart from each other electrically because the windings are mechanically apart from each other. Okay, some advantages of the revolving field type is we can get really high voltages and really high current ratings out of these guys because what we have is the windings are fixed. So the stator windings can be quite large, okay, and we can get a lot of turns on them. Remember our BLV formula, E generated equals BLV. Well, we're going to look at that in a few minutes. We can actually get, if we have lots of windings or large windings here, we can get high currents and high voltage out of those windings. Hard to do when we have to pass those three-phase lines through slip rings. Okay. We have two types of rotor designs that we're going to look at too. Okay, aside from having a rotating field or rotating armature, we have a salient pole rotor or a cylindrical rotor. Okay. Okay, here we have a salient pole rotor. Now, salient pole rotor alternator, okay, it's, as you can see in the picture here, you have these wound poles situated and in a large diameter. So these type of rotor design, it's more thinner, but the diameter is a lot larger. Okay, so as you can imagine, when we're rotating this, the forces that are exerted on this can be quite large. Okay, these type of salient pole rotors are often, always used for slow speed applications. You can see texts that say sometimes these get up to 1800 RPM. I've never seen one. The rule of thumb I go to is if it's less than 1200 RPM, that's the speed range these are going to run at. Now, these type of rotors, BC Hydro used in some of their hydroelectric dams. Okay, slow speed applications. The other type is the cylindrical rotor. Now, you can tell it's a lot different. It's narrower in diameter, but it's longer. Okay, so high-speed steam turbines, they use these guys. Diesel electric generators, or diesel electric alternators, they use these cylindrical rotors. Okay, they're for high-speed applications, anything over 1200 RPM. So whatever the salient can handle, these guys will handle. Okay. Okay, as you can see here, to generate three-phase AC, we need a rotating fixed north and south pole in our field poles, our rotating field. So to achieve that, we have to use DC in our field windings for our rotating field poles. Okay, as we saw on the previous slide, we need a fixed north and south pole rotating in the center of our three-phase alternator. To get these fixed poles, we have to supply the field with a DC source. Okay, now there's different methods of supplying the DC. We're going to have a look at a few of them. Okay, before we carry on a little further, I just want to point out the way the fields are. We have a little bit of a safety component here called a field discharge resistor. So we have an external DC supply on the right here from a thing called an exciter. That supplies the DC to our DC field in our alternator here. Well, when we open the circuit to isolate it, we have a DC coil here that's going to have a collapsing magnetic field. That's going to create a high potential across the opening contacts here. So this has been designed with a field discharge resistor. So what happens before the contacts in this switch open, the resistor is going to get paralleled to the field winding here and give it a discharge path. And then when we open the field switch here, it's not going to do any damage to the contacts and it won't arc. Now, frequency of generated voltage. So you guys, this is probably old hat for most of you. Most electrical systems, all electrical systems in North America runs at 60 hertz. Okay, to ensure output voltage from alternators remains at a constant 60 hertz, precise controls must be in place. So what determines frequency, guys? Okay, you remember our frequency equation, number of poles times the RPM of the generator divided by 120 is going to give us our frequency. Or if we wanted to know what the RPM of a motor was, we use a transposed version of the same formula. Well, right now with the alternator, well, we want to be able to control the frequency, okay? So the F is our frequency, so the only way we can control frequency on an existing operating alternator is to adjust the speed of the prime mover. Okay, adjusting the speed is the only way to control the frequency, only easy way to control the frequency of the alternator. So how that's done is we have speed governors on our prime mover. What that looks like for a diesel generator, we have a throttle control on the diesel motor. Okay, for steam turbines, we have flow rate for the steam going through the turbines. For water, we're going to control the water flowing through the hydro turbines. And then for wind generation, we often control the blade pitch for the wind generator to control the RPM of the wind turbine. Now they all have feedback loops here to control the speed of the prime movers, and we're going to have a look at that a little later on. Now, voltage generated. We prefer to have a constant, consistent voltage out of our alternators. Okay, so this is where our E generated is BLV comes into play. And there's another formula that you're going to see also. E generated equals K times flux times speed. It's the same formula, okay, except we have a few different symbols there. Functionally and logically, they're identical. Okay, so if we want to control our voltage, output voltage of our alternator here, okay, well, if we control the velocity, what's that going to do to the frequency? Okay, it's going to mess with our frequency. We want to keep our frequency at 60 hertz, so we don't touch our velocity. What we're going to do is we're going to play with our flux density, okay? Our flux excitation Webers on that side, flux density over here. How do we do that? Well, we control the current going to our field coil, our rotating field coil. Okay, now, side note here, the automatic control for voltage is usually done by a thing here for diesel generators at least. Use this thing called an AVR, which is a automatic voltage regulator. Okay, and that's the means of automatically controlling your output voltage of your generator. Now, how that works is the AVR is part of a feedback loop. Okay, when I talk to you guys about feedback loops, what I'm saying is it's a loop of we have a desired output voltage here in our generator. We're going to have sensors measure that voltage. Those sensors are going to send a signal to our AVR, our automatic voltage regulator, and it's going to have a setting in it that says, okay, we want this voltage at, for example, 600 volts. Okay, the voltage sensor, if it sees our voltage is dropped below that tolerance, our sensor is going to send a signal to the AVR. The AVR is going to say, hey, our voltage is dropped below tolerance. Send a signal over to the excitation system and goes, hey, put some more excitation current through your field winding. Make your magnetic field, rotating field in your alternator stronger because we want to generate more electricity to send out of our alternator here. Now, when we do that, we're in our E generated equals BLV, we're increasing our B, our flux density, okay, which is going to make our E generated go up. And then the opposite is true. If it senses the voltage goes a little too high, the voltage sensor will sense too high a voltage. The AVR is going to say, okay, throttle back. It'll tell the excitation system to go, okay, reduce our current through our field coils, and then it's going to reduce the amount of flux density that is rotating through the windings here, and it's going to reduce our voltage. Okay, and typically these AVRs, they're not going to run at exactly 600 volts or one specific voltage. They're going to run in a small range. So you could see these go from, like, if it was a 600 volt generator, it could be bouncing up and down. It'll try to bounce up and down between, 595 to 600 or 593 to 600. Typically, they don't want to go over voltage because equipment doesn't like it when you over voltage sometimes. Now down here on the bottom, we have our frequency control loop. Okay, so we have a frequency sensor here, okay, connected to our lines, our output lines of our generator. And it's going to sense frequency. The load frequency controller here, the LFC, okay, it's going to say, okay, we're not 60 hertz, or we're too high, or we're too low. And if the frequency goes too low, our valve mechanism here, for this one's a turbine, it's going to open up and allow more steam to go into the turbine and speed up our generator. Okay, so it's noticing the frequency has dropped down, so it's going to speed up our generator. Well, our generator is sped up. What happens? Our voltage sensor, it's going to detect that increase in voltage, so it might have to change, throttle back the current a little. So we got this little loop here where the system has to continuously update itself and correct itself to maintain our proper outputs from our alternator. Okay, now we have a couple different types of exciters to be aware of. There's brushed exciters where we're going to have an external, let's hypothetically say this is an external power supply and this is the rotating field that's over here. Well, to connect our stationary power supply to the rotating field, we'll need slip rings and brushes. That's one option. That's a brushed power supply. This is a brushless power supply. So how does that work? Well, we have our DC field coil here that's on the rotating rotor. We have on the same shaft that the rotor's on, we have a three-phase rectifier. Have a look at this three-phase rectifier here. We've got 1, 2, 3, 4, 5, 6 diodes. Pay attention to how they're connected here. You're going to need it in electronics. We have current flowing, a negative over on this side. We're going to have current flowing this way through these diodes. Well, then we have our three-phase lines over here. We have a rotating AC rotor. So we have a rotating armature type of little generator here, okay? And that's fine. That'll work. All we need is small amount of current here. Remember, we have lots of windings on our rotor field over here. So that's going to accommodate the lower current. Okay? We don't need as high current because we have lots of windings to be able to create the same flux density. Now, this rotor that's rotating, now what's turning the whole mechanism? Our prime mover, our diesel generator, our steam turbine, whichever mechanical component is turning it, is turning the whole mechanism. So this AC rotor is spinning. It's got a Y connected windings there. Stationary beside these windings, we have one DC field pole, right? As our exciter field here. So what it does is it creates a north and a south pole here that this Y connected rotor is going to be passing through, and it's an AC, it's an alternator, right? So it's going to create AC, three-phase AC that's going to go into our rectifier. We're going to rectify it through our three-phase rectifier and convert it back to DC here. Now, the beauty of this is there's no contact moving parts outside of the bearings. We don't have brushes or slip rings anymore. Low maintenance. Okay? Now, how do we control the current on this one? Well, our AVR would be incorporated over here where we have this field rheostat. So this is a pretty crude and elementary way of controlling our output voltage from our alternator. We have our output supply from our alternator. It's powering our rectifier here, okay? And our rectifier is sending DC over to our DC exciter field. Our exciter field excites into our AC rotor here. Our AC rotor has three-phase going to our rectifier, back to our DC rotor field, rotating field here. Now, if we control the current or the magnetic field strength here, we'll control the the induced voltage in our Y-connected AC rotor, which is going to control the amount of voltage we're going to put across our DC rotor here. Okay? All connected. Now also, when this initially starts up, sometimes there might be a small battery because let's say this is rotating and there's no generated voltage. So often you might see a battery connected across the positive and the negative here. Here's an actual shop manual from, I believe it was Cummins Diesel, and I believe I stole this from the port when I worked there. Showing exactly how they work. We have our exciter field winding, stationary DC coil here going through our bridge rectifier. We have a little booster transformer with this low impedance coil here, just to give it a little power instead of tying it right into the lines here. And then this exciter rectifier, it sends the DC to our coil here. Our coil creates the magnetic field that our three-phase AC exciter armature winding here is going to be passing through to create its three-phase potential. And then that runs through our bridge rectifier assembly here, which actually looks like this. They don't look like diodes when you have a look at them. And then we got our DC coming out of there. Okay, and then our DC is going to go through our generator field winding here. It has many, 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 many turns, so we can have a very high flux density. And then that's going to be rotating. Then we have our stationary generator stator winding here, Y connected. Okay, and it's going to be stationary with our magnetic field passing through the windings. Okay, nameplate data. Now let's have a look at this nameplate here. Type of information, it's similar to motors. Okay, very similar. We're going to have the model number, the serial number, the output volts. Okay, phases, three-phase. We're going to have kVA on this guy though. Okay, why is that? It's because we're going to have, same reason for transformers, the power factor is going to vary on our connected load here. And then we're going to have watts, and that's used to determine actual kilowatts used. Okay, typically for determining also the prime mover ratings. We have our power factor. That this is actually going to have some power factor to it, so it's going to have that listed. Our amps, frequency output. Now the DC volts range, it's going to have that maximum amps, and temperature rise in the temperature rating, and the operating RPM. Now that may go up and down a little bit because we have to maintain our frequency. So typically it should run at, if it's a 2-pole alternator, it should be at 3600 RPM to get our 60 hertz. Same rules we had with our motors, but backwards. Alternator loading. Okay, all alternators have some resistance and inductance inside them, right? So a combination of those, we call it's the internal impedance. Okay, now what's going to happen when our current increases to our loads is we're going to have more current going through our alternator windings. That's going to give us some voltage drop in there. Okay, that voltage drop is going to affect our terminal voltage. So as load increases on our alternator, our output voltage is going to decrease. Same concept as transformers. And so we can calculate our voltage regulation as follows. We got our no load volts minus our full load volts divided by our full load volts times 100 will give us our percent. So here's a beautiful graph showing that relationship here. So as if we have a no load, and that's a pretty realistic voltage level of 4800 volts for our generator. Let's see, this might be a BC Hydro generator, alternator. Okay, at no load it might operate at 4800. And then as we load it up to fully loaded, our voltage drop might drop down to 4160 here. Okay, so our full load voltage is going to be 4160. Now sometimes we're going to operate it higher because BC Hydro, these alternators might have to transmit electricity for a long distance before without going through transformers, so they might take up that voltage drop of the lines into account and over excite their field in the rotor circuit to overproduce the voltage, so we can have a reasonable amount of voltage level by the time it gets to the end of the lines. That's if there's no transformers, but BC Hydro is going to step their voltages up to 500 kV, send it down this length of BC and to the lower mainland from up in the Peace Country. So anyway, back to voltage regulation. So here we are, we have a 4800 volt no load, 4160 full load. Well, 4800 minus 4160 divided by that, we're going to have a 15% voltage regulation. Now, common connections for these guys, pretty straightforward. Same concepts that you're looking at with three-phase motors. Okay, here we have a series Y high voltage connection. Okay, so when we're running at rated RPM, each of these windings here is going to kick out how much voltage? 120 volts each winding. Together they're going to be 240. Now line to line we're going to have 416. So if you have a look at this here, series Y high voltage connection for 240 416. It's Y connection, so we're going to say phase and line voltages here. Okay, and you see the dot dot dot, yeah, that's our neutral. Okay, we want to have that return path. We don't want our system to get all out of whack because of no neutral reference point. Here we have a parallel connection. So again, same windings now are spinning at the same RPM. We're going to have 120 volts induced into those. Remember, these windings now are sources. Okay, so it's just imagine you're connecting batteries up. So right now we want to have an output of 120 208. Well, if each coil is rated for 120 volts, we're going to parallel them up, and then if we connect line to line to this Y connected parallel system, we're going to line to line, we're going to get 208. Okay. Now we have a delta high voltage. Okay, so same windings, let's say they're 120 volts. Well, what are we going to have? Well, to get our 240 volts out of it, we have to series these up, and we're connecting a delta connection. Okay, and let's say our maximum line current is going to be 173. Previous slide, our maximum line current was what? Did you guys catch that? 100 amps. Parallel delta low voltage. Okay, each coil, remember, is 120 volts is getting induced into it. So we parallel them now. So we're going to get our line voltage is going to be the same as our phase, okay, which is going to be 120 volts. Now because we paralleled them, look what happened to our current. It doubled, okay, because we're maximum current we can get when these were at the high voltage connection was 100 amps through each windings, okay, and our line current was 172. So now we parallel them because the maximum we can put through each coil is that amount, and now we can double it to 346. Awesome. Now let's have a look at how we operate alternators in parallel. Okay. Now, if you have, it's pretty common to add another alternator to a system, increase your capacity, okay? Because you don't want to underutilize your alternator. So you always want your power system to operate at its top 20% of its capacity. Things are more efficient, as you notice with motors. They run best when they're close to fully loaded, better power factor. Everything's more efficient at those higher end designed regions. So if you want to parallel an alternator, because let's say you have a system where your load is inconsistent over the week, so sometimes you need more power added to your system. You might need to have an instance where you're going to parallel an alternator and bring it up to speed to help boost the amount of capacity. Or also, a little more common here in the Lower Mainland is when you're tying in a freighter in the dock, we have shore power now, and those freighters actually plug in, and in the ships, they synchronize their ship's power to the BC Hydro power. So they go through this process we're going to look at. Okay. Number one point here we need is our frequency must be the same. Number two we have to look at is our phase order must be the same. Our voltage must be the same, and our voltage must be in step with each other. Okay, we're going to have a look at these right now. So our frequency has to be the same because you have a look at this waveform right here. Where are you? Okay, we have our generator 1. Let's say that's a nice 60 hertz system. Generator 2, that looks like it might be might be 75 hertz or 80 hertz. Well, let's see what's going to happen when we're out of phase. We're guaranteed that if this was A phase from generator 1 and A phase from generator 2, they're out of phase from each other because they're not going at the same speed. So we don't have the ability to bring them in phase and a thing called in step yet. Okay, and by in step I mean the peaks happen at the exact same time. We're going to look at that. Okay, so what has to happen is we have to adjust the speed of our prime mover to adjust our frequency. Okay, now that those closed loop controllers, they might have an external input to them, so you can tweak the frequency. Okay, so here we have a thing called a frequency meter that you can watch while you speed up and slow down your prime mover that's powering your alternator. Okay, and then your goal is to try and get the frequency, and hopefully the system you're connecting up to has a frequency meter on it, so you can make your frequency exactly the same. Okay, also you're going to see this thing called a synchroscope, or you could see it. How this works is you're going to have the incoming alternator connected on one side, your running bus on the other, and it's going to tell you if your frequency is more faster or slower than the running bus, and it's going to rotate one way, which would be clockwise for faster, counterclockwise for slower. As they get closer to the same frequency, it gets slower, the rotation gets slower until it stops. And then once they're right about at this index point here, and there's a couple other sensors we're going to look at, you can lock these two generators in. Our goal is to lock them in. Okay, voltage must be the same. Okay, one of the oncoming alternators is up to proper frequency. Will have to be adjusted to make sure the voltage is the same. How do we adjust the voltage of an output of an alternator? Well, we adjust the field strength of the rotating field in that alternator. Okay, so we'll dial that up and we'll make sure we have 2 voltmeters, one of the existing system, one of the alternator, make sure those voltages match. And I'm going to show you a video of this. It's pretty cool. Okay, phase order must be the same. Most systems have things called synchronizing lamps connected across them. Okay, let's see if my laser pointer here works. So if you look here, the number 2 here, that's the alternator we're bringing online. Okay, it's tied into the existing bus of the system. Okay, and those are the main switches that once everything's proper, we close those and bang, it locks in the alternator. And when they're locked in, it's pretty cool because the alternator will follow the existing bus. They stick with each other and all the values stay the same. It's pretty neat to see. But before that happens, if we have our phase order is out, these 3 lamps, okay, they're going to be flashing. Now remember, if you remember the previous slide, we saw the different peaks of the frequency waveforms were not in phase, okay? So imagine if that was A phase. The potential difference between the 2 peaks is like the same as measuring the potential difference between 2 phases, phase A and phase B, let's say, and you're going to have a line voltage equivalent across those. Well, that's what these lights are going to see. Okay, so when there's a potential difference between the T3 phase here and this phase of our existing bus, okay, the light's going to go on. If they are in phase and in step, the lights are going to be out, okay, and the frequency is going to be the same. But if they are not in phase, if the phase order is out and they're not in step and all that, these lights are going to flash at different intervals. It's going to look like a little bit of a light show. Now we're going to see that later. Okay, voltage must be in step. Okay, now this is the thing that's going to throw the lights out the most. So right now, if let's say we have we adjust the phase order so all 3 phases are in the same, all different power sources have the same phase order, ABC and ABC. So what's that going to look like with these lights? Now that these lights are connected in the same phase order, they're A phase on both the existing system and the generator, if you see here, the two waveforms, they're slightly out of phase. So, okay, two A phases are out of step. They're out of step with each other. Now the B's are going to be the same, and the C phases are all going to be the same. And they're all going to be out of step by the exact same amount. So what happens now, and why these lights flash is we haven't got the frequency perfect yet. It's very hard to get the frequency exactly spot on. It stays there. One's always going to hunt up and down a little bit. So what happens is, because one of them's slightly out of frequency, it's going to overtake the other, and this one waveform is going to pass it. So when they're perfectly in line with each other for that short amount of time, the lights are going to be out. Then they fall out of step with each other, the lights go on. And that's going to happen. So you're going to see all three of these lights flash on and off at the exact same time, because all three waveforms are exactly 120 degrees out of phase with each other, and they're all going to fall in and out of step at the exact same time. Okay, and then just here's a great diagram of a whole system all connected up, where we have our alternator 1 and our alternator 2. We have our synchronizing lamps here. We have our synchroscope connected up to measure across. Okay, we have our rheostats to control our excitation field inside our alternators for both of them. Okay, we have an ammeter and voltmeter and frequency meter, right? So we need all these instruments working so we can figure out if we can parallel them or not. All right, and so how this system usually works is this will be the standby generator. We'll have this guy up and running all the time, and we want to take this guy out of service so we can do maintenance and put our standby on. Well, we got to make sure that first thing is get our frequency close. Next thing is we'll get our voltage by adjusting our adjust our frequency by adjusting our prime mover speed. Adjust our voltage here, our output voltage, by adjusting our field rheostat. And then once we get that, we confirm that our phases are in the right order. ABC, ABC is ABC, ABC. And then we got to speed up and slow this down to get our two systems in step, which is our synchroscope's going to rotate at a certain speed and then stop once they're in step, or once the frequency is exactly the same. And then these lights will all be out, and then we can close this disconnect. They're both in parallel, and then if we want to open this one, we're free to do that, do our maintenance. And then the tricky thing is getting this back online, because we don't have lights on this side. But anyway, that's for another time. Thank you very much, guys. Now, hopefully you can watch the video for this.